knows a lot about the science stuff. Professor Dave explains.
Polyethylene and polypropylene together represent over 50% of the plastic produced in the world. Specifically, the chemical industry produces around 100 million metric tons of polyethylene, PE, and 60 million metric tons of polypropylene, PP, each year. The raw materials for these polymers are ethylene and propylene, gaseous olefins obtained via steam cracking of hydrocarbon feedstocks. As these substances are produced from non-renewable sources and are essentially non-biodegradable, they have acquired a bad reputation lately due to the pollution of the environment caused by their indiscriminate disposal. Their devastating effect on all life forms is being elucidated by a host of current publications. Long-term, these are clearly products humans will have to do without. Currently, however, PE and PP markets are set to grow 3 to 4% per year until 2035. The plastic pollution problem could be minimized by proper recycling or better disposal procedures. However, we are far away from an optimal situation, as many countries handle municipal waste through landfills, causing a huge environmental problem. Among industrialized countries, India disposes of municipal waste through landfills to an extent of 70%. The US recycles 5 to 6% of its used plastic, and 50% ends up in landfills. Some developed countries, like South Korea, Germany, Austria, Slovenia, and the UK, have reached over 50% plastic recycling and have abolished landfills. Most developed countries have, at least on paper, aggressive targets in plastic management, but the problem created by the overproduction of PE and PP is still far from being resolved. In terms of industrial and economic development, however, it is hard to imagine a modern industrialized world without plastics. Plastics have played a major role in promoting our current lifestyle, and their development has been highlighted as one of the most impressive achievements of science and technology. Polyethylene was first described by von Pechmann in Germany in 1898. His method was not practical, and his PE did not receive applications. PP was first prepared in 1951 at Phillips by two U.S. scientists, Hogan and Banks, also through a method which was impractical. What are the structures of these two polymers? PE is just a long chain of methylene groups and indeed was initially called polymethylene. Polymerization of ethylene with a suitable catalyst will yield long chains of methylene groups, the length depending on the conditions of the reaction. The same is true for propylene. Here, however, we have a stereochemical problem. PP can have different stereochemistries. PP is atactic if the methyl group's configurations are randomly distributed. It is called isotactic if the absolute configuration is the same at each methyl-bearing carbon. It is syndiotactic if the absolute configuration alternates regularly. The most desirable properties of PP are exhibited by the isotactic polymer, and currently available PP is 85 to 95% isotactic. This material became available with the development of the first modern catalyst for olefin polymerization. The first catalyst which was practical enough for large-scale production was discovered in 1953 by German chemist Carl Ziegler, working at the Max Planck Institute in Mulheim. Italian chemist Ziegler-Natta, working at the Politecnico in Milano, was able to extend the polymerization to propylene, and reported the first scale-up of the process. Ziegler and Natta shared the Nobel Prize for Chemistry in 1963. Their chemistry is remarkable, therefore it is worth describing in some detail. For the historical details of this discovery, we will rely on the testimony of J.J. Eich, professor of chemistry at the State University of New York at Binghamton, who was working in Professor Ziegler's lab at the time of the discovery. Ziegler was interested in the organometallic chemistry of main group metals, and had carried out pioneering work with organolithium compounds. He had noticed that alkyl lithium compounds, under ethylene pressure, add up to 15 units of ethylene in a carbometallation reaction, yielding long-chain hydrocarbons after a final acid quench. Although the reaction was not clean, also producing resins and terminal olefins, Ziegler recognized the potential of alkyl metal compounds to undergo sequential carbometallation and potentially lead to useful polymers. Moving to other main group metals, Ziegler focused his attention on trialkyl aluminum compounds, which are extremely pyrophoric compounds, meaning they ignite spontaneously when exposed to air. This is because the carbon-aluminum bond readily oxidizes in the presence of oxygen gas. It was found that triethyl aluminum in hydrocarbon solvents adds readily to ethylene under pressure at 100 degrees Celsius to yield high molecular weight trialkyl aluminum compounds. These, upon oxidation, yielded a statistical mixture of long-chain aliphatic alcohols, which find use as active ingredients in detergents and other products. The result was rather surprising because trialkyl aluminum compounds, usually prepared in ether solvents, were considered quite inert to carbometallation reactions. The explanation is that trialkyl aluminum reagents are strong Lewis acids, and they form a tight complex with ethers, which are very good Lewis bases, and these complexes are quite unreactive. Working instead in hydrocarbon solvents unmasked new reactivity patterns for these compounds. At this point, a fortuitous failure led to a key development. One day, the polymerization reaction failed and instead yielded 1-butene gas, obtained by an apparent beta elimination of an aluminum hydride. The troubleshooting analysis indicated that traces of nickel in the autoclave may have been responsible for the anomalous result, meaning that traces of a nickel catalyst promoted a new beta elimination reaction. This was indeed confirmed experimentally. In the 1950s, the chemistry of transition metals was in its infancy, and their catalytic properties were just beginning to be discovered. The reasoning was that perhaps one could find a transition metal compound which could catalyze the polymerization reaction. The experiment using catalytic amounts of titanium tetrachloride with triethyl aluminum hit the jackpot. Polymerization rates were improved by many orders of magnitude, and polymers with molecular weights of up to 3 million were obtained at room temperature. These were the first samples of modern PE plastic. Naturally, Ziegler decided to patent the invention. In the meantime, a licensing agreement had been signed with the Italian petroleum company Montecatini and their consultant Professor Natta. Natta and Montecatini extended the polymerization to polypropylene, another plastic which turned out to have immense commercial potential, and changed the catalyst from TiCl4 to TiCl3, which made the chemistry more effective. At the same time, other companies were experimenting with similar chemistry, and a huge patent battle ensued for the rights to the chemistry. It was a legal battle without precedent, which lasted decades. Only in 1982, long after Professor Ziegler's death, did the Max Planck Institute win the battle and was awarded damages from companies deemed to be violating MPI's intellectual property rights. Over the last 60 years, the search for new catalysts has been intense, and there are now dozens of effective catalysts based on a number of transition metals. The mechanism has been studied using titanium and zirconium cyclopentadienyl complexes, which are homogeneous systems which facilitate the reaction. In a simplified scheme, the metal-chlorine bond of the catalyst is replaced via the aluminum reagent to yield a metal-alkyl bond, and these species are converted in situ to cationic titanium or zirconium alkyls, which insert ethylene or propylene at a rate many orders of magnitude faster than the carbon-aluminum bond of aluminum compounds. Termination is a complex process which is carefully controlled. It can be spontaneous, such as by beta hydride elimination, or induced, with hydrogen gas or acids. Of course, chemists have extended this process to other olefins and even mixtures of olefins, giving rise to new polymers and copolymers. In addition, catalyst development is still a fertile area of research, and new systems continue to be developed, patented, and implemented on scale. In general, however, it was the serendipitous discovery by Ziegler that transition metal alkyl reagents can polymerize olefins very efficiently, which opened a fertile new area of research, leading not only to a host of publications and mechanistic studies, but also to important commercial products. As often occurs, the scientific breakthrough was triggered by an unexpected result, and this highlights the value of the famous dictum, "Luck favors the prepared mind." Ziegler did not overlook an anomalous result, but investigated it and capitalized on it, achieving a scientific breakthrough worthy of a Nobel Prize.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.